Okay, good morning. I just had a small accident. Why lay down my screen and my network connection got disconnected. Okay, so we're back to a normal life. Let's continue what we discussed yesterday. Is the integral form. Can you hear me, Tan Xiao?
Yes.
Okay. Let's continue the discussion of integral form of Maxwell equation. Yesterday, we introduced first Faraday's law. Then we also introduced a very significant contribution discovered mathematically, right? That is a generalized Am's law. Okay. So Am's law compared to the Am's law that only concern a current that doesn't change with time. When the electrical field changes with time, we need to introduce another current. Okay, we need to introduce another current. So that current we call displacement current. Okay, and from this generalized Am's law, we can prove another relation. If we have a closed surface, then we have a current integration, current density, right? So the flux of the current go into from a part of the surface and go out from another part of the surface, right? So this equal to the flux of electric field flux density, right? So this relation also consequently, this relation is the net current. The net current that going out from a node, see, okay? Going out from a node. So this is how fast a charge accumulated in this node depleted, okay? Go away or decrease. So it's the same rate, right? And this is a relation we have discussed yesterday, right? Okay. Let's continue the integral form. Then next hour we discuss a differential form. So we also can experimentally find another important relation is the flux, the total flux of electrical field, okay, equal to the total charge included inside this closed surface, okay? So if this is the charge, if this is charge, then we have a surface enclose this finite volume of charge. Then we can find this relation. This independent to what geometry of the surface is. Okay. Doesn't matter how far this surface is. Okay. So that is a way we can measure. That's the way we can measure how much charge included in the surface, right? Then how to measure it is if I can have imaginary surface, okay, then I can measure all the flux, electrical field, okay, going out of this surface, net, right? Net contribution, net flux. Okay, so net flux. Then if we have a net flux, then if we can collect a net flux, we know how much charge included in this surface, right? So this we call name is a Gauss's law, okay? So whenever we call Gauss's law, we are dealing with the collection of the total flux of a field. Okay, so Gauss's law relates to the flux. Okay. Then also, if the charge density, if the charge distributed over a certain volume, surface, or a wire, a line, okay, with a certain density function, then we need to do the integration to find the total charge, right? So this is if we know the volume distribution of a charge, we do the volume integration, we know this is total charge, right? If this is a perfect conductor and charge only exists on the surface of a conductor, then we do the surface integration, okay? Whatever means you take, we collect the total charge, okay? We collect total charge. Then if this is if we consider charge distribution, so this law we can write into the integral form. This is a more generalized integral form, right? Okay. So this is Gauss's law for electrical field. Okay, let's say Gauss's law for magnetic field. So just now we said, okay, whatever we call Gauss's law, that's something deal with the collection of flux of a field, of a field, all right? Just now we collect the flux of electrical field. Now let's collect a flux of magnetic field, okay? So when we collect the magnetic field over a closed surface, then the experimental result tells us we get nothing, okay? We get nothing, okay? That means this net flux is always equal to 0, okay? Of B, okay? So we don't call magnetic field, we don't write the magnetic field too long, we just use B, right? So that means magnetic field, the net flux, no matter the surface is in what geometry, how large or how small, okay, then the net flux is always equal to 0. Then compared to the Gauss's law for electrical field, on the right-hand side, we have a charge, that is an electrical charge. Now for magnetic field, on the right-hand side, we get nothing. What that means? That means there's no magnetic charge exists. So if we look at all the phenomena that concern magnetic field, okay? So you can see either the magnetic field generated by a current wire, okay? Then if you have a very small surface, if you have very small surface, you always see the field go into the surface equal to the amount go out of the surface from different parts of the surface, no matter how small it is, right? So no matter how you generate magnetic field, even generated by from the south to north pole of the globe of the Earth, right? So the magnetic field, the line is always a closed line, okay? It's always a closed line, okay? Not like electrical field. Electrical field from the charge going out, never come back, okay? Never come back. You won't see, oh, the field going back, no way, okay? You never can say this, never can say this. So this is the identity of electrical field and the magnetic field, right? If I show you some of the field line, then you should be able to judge, hey, what field is this, right? Because identity is very obvious, right? So we call this law, we call Gauss's law for magnetic field, all right? And later on, okay, we don't prove from integral form right now, but it's much easier to justify when we deal with integral form, when we deal with differential form of Faraday's law and Gauss's law. The conclusion is the Gauss's law of magnetic field can be derived from Faraday's law. Okay. Then the Gauss's law for electrical field can be derived from a general Ohm's law. Okay. So that is derived. But we don't discuss this in integral form. In differential form is just by 1 second. It's obvious. Okay. Then from Gauss's law, and also from Gauss's law, and also what we have learned yesterday, we derive from the Ohm's law. Okay, we derive from Ohm's law. Is this part, according to Gauss's law, the flux of D equal to what? Equal to total charge, right? Is equal to total charge. So therefore, this relation we said we can write in this way, right? The total charge. So if we consider this, not surprisingly, this is the total Q, right? Not surprisingly, this is total Q. Okay, so we gave a name, we call this is called the conservation of charge. Okay, so that means once the charge decrease, where the charge goes, the decreased charge form a current flowing out of the surface. Okay, flowing out of the surface. But if the opposite way is once the charge increase inside the volume, that means where the charge coming from outside. So that means the current go in, the current go in. So that's why we need to have this minus sign. Okay. Once the charge decrease, current go out is in positive direction. Right? Then when the charge increase, that means current go in the negative direction. Okay, let's take a look at some of the very ideal example. Okay, let's suppose we have a charge put at the origin. Okay, we have a charge put at the origin. Then this charge is a function of time. So that means the charge will change with time. If charge will change with time, that means you may either increase or decrease with time. So if decrease, that means we have a current going out. All right. So where does the current go? We assume, suppose the current can go in any direction, right? So let's say the current go along the Z direction. Okay. So if the current go in that direction, then what this question is, can you find can you find this? Oh. Can you find this? You find the loop C. I didn't specify what C is. Okay, then you have a magnetic field intensity H. Okay, magnetic field intensity. We defined H, right? We defined H. All right, so the H is flux density divided by permeability, right? Okay, so let's do a line integration. This quantity has a name. We call circulation, right? You see, because when you have a line integration, it's always enclosed, right? So this is a closed contour integration. So we measure how much circulation it is. Okay, like if the field in a swirl shape, then you can see their line integration has a net value. Otherwise, you may collect nothing, right? Okay, let's calculate this. Okay, once we ask to calculate this, that remind us, hey, should we consider a general Am's law? Okay, but because Am's law relate to this circulation of magnetic field with a current, right? And also with the description of a time variation of flux density D. Okay, electrical field flux density. Then if we consider this, then we better relate D with the charge, because we didn't give D, but we give charge. But however, we know the D and the charge are related, right? And the D and the charge are related, but this relation is with a closed surface, okay? This is a closed surface. But now our problem, we have nothing to do with closed surface, but we can define a very special surface, which is a semi-sphere, okay? I imagine I have a semi-sphere, and also I specialize this contour C is a circle. This circle lay in the X, O, Y plane, X, Y plane. Okay, this C sit in X, O, Y plane. Okay, I treat the special case first. Okay, I treat special case first. Because this C is a circle, then I can imagine I have a cover. This cover, okay, bounded by the C, but this is a semi-half sphere. The things I use semi-half sphere is because when the Q put in at the point, the flux line, electric field line, must be in radial direction uniformly across a sphere. Right? Then if I use a semi-half sphere, then I have sufficient reason I can say this, okay? Because this S is a half of a complete sphere. If I use complete sphere, then I know the total charge inside is Q, right? Then the flux over a semi-sphere or half of the sphere is half of the Q, right? So that is a relation we can use. If we can use this relation, we need to relate the flux of D related to the current going out, right? And then earlier we mentioned, we know the total current created by the change of the Q. that is the conservation of charge, right? Conservation of charge. Follow this relation. Okay, follow this relation. Then we substitute this into this. Then we can easily, we have this. Okay, so we replace this. We replace this by minus I. Okay, by minus I. Then we know A. We know the circulation of a magnetic field, okay, equal to half of the current, right? Equal to half of the current. And also, when we draw this conclusion, okay, really it's independent to what this circulation, this C, how the C is put, right? I can put in any surface, okay, along any plane, right? And this result is also true, right? So then we understand, so this result is true for arbitrary contour C, okay? So for arbitrary contour C, the circulation of magnetic field, okay, circulation of magnetic field equal to half of the current, okay? Because in this case, we assume the current only go half of the semi-infinitely long direction, okay, the current. Okay, so the next question, so next example, let's look at if we have an infinitely long line charge, okay, if we have infinitely long line charge, and the infinitely long line charge, what we like to do is we like to calculate electrical field at any point. Okay, at any point, tell me what is electrical field. The magnitude and the direction. Magnitude and direction. So in this case, let's say if we have infinitely long line charge, infinitely long line charge. If we only look at, say, a symmetrical, let's say we look at this, if this point is what we are interested in. If we interested in this section, the contribution, that according to Coulomb's law, this is a partial field generated by this very small, section, right? Then I always can find another point. I always, right? Okay, this is another DL. Okay, if I call this equal minus DL, okay, just give a name. Okay, minus DL. This DL also can find the field. So this E is created by minus DL. All right. So as a result, this field has component in vertical direction and in radial direction, right? And the other field also has a radial direction, but in the opposite vertical direction. So these two always cancel, right? Always cancel. So as a result, we only can find, as a result, I only have the electrical field in radial direction, right? Because for any point, I always can find half and half, right? A symmetrical case. So in this case, we can find, we take this point along z equal to 0, right? It's just arbitrary point. Then we can do the integration. We can do the integration from 0 to infinity. Okay. Then Gauss's law gave us some advantage we can take. What advantage is that whenever you find a symmetry, of field, whenever you can find the symmetry of a field, you can think of Gauss's law, right? Just now we use example that is deal with Gauss's law, right? We deal with the Gauss law of electrical field. Now we can use Gauss law for electrical field. In this case, is we define a cylindrical surface, okay? Cylindrical surface with length L, okay? And we know, okay, because the line charge is infinitely long, we have null field go out or in from the top and the bottom surface, right? Because we only have a component in radial direction, okay? We only have electrical field in radial direction, okay? That is the only field we have. Then we can think about the Gauss's law. The Gauss's law tells us is the flux of D, right, equal to a total charge inside this surface. Now, even though we consider finite height for now, okay? Finite height for now is if the charge distribution is uniform, okay? It's uniform charge distribution. So the total charge is charge density multiplied by the total length. This is the total Q, right? This is total Q, right? Then let's do the integration. When we deal with this ds in cylindrical coordinate system, what's that equal to? That's called the radius times d phi. This is the arch, the length of the arch, right? Then times dz is the height of the differential area, okay? Then what is direction for cylindrical coordinate, okay? Then the direction for this delta s is in r direction, okay? This is what this is, okay? This is what this is. This is ds, right? So once we have the ds, we also know the normal component in r direction is only function of r, is independent of the angle, right? Uniform, right? So we put r is a function. So this is my vector d, okay? Vector d. And we are concerned because that component is 0, right? Then this is ds, differential area. Then we dot product, then the dr dot dr, because this is a unit directional vector, okay, that equal to 0, right? Oh, sorry, that equal to 1, Z equal to 1. So this flux, total flux, can be obtained by integration, or because this is everything is uniform, so integration is just multiply the total length of L. Okay, the total length of L. And then you will see, oh, this has nothing to do with our question because our question is infinitely long charge density, right? Sure. Infinitely long, let's find the finite length first. The finite length, for finite length, we know we have a function of L, right? But we also have L, you see, we have L here, we have L here. So L is canceled. Okay, then our result is the D, R component, only depend on the distance, R. Okay, only depend on the distance R. Then you will ask me, where we reflect infinitely long condition? Of course, we use, don't forget, if we have finite length, if we have a finite length of charge, then how you find the field? How you find the field is here. Then you must have Z component as well, right? And not only just R component. So that means we already use infinite long condition. Okay. Then from infinite long condition, we draw the conclusion that the field only has R component, right? And then also the field is uniform, is independent of the direction of phi, and also the location. Also, we use Gauss's law. We can use the Gauss's law. We can find the magnetic field, okay. Let's say we have a problem is we have a conductor. This conductor is a very thick conductor rod. Okay, the conductor has a uniform current distribution. Okay, the current distribution, the current flowing in the Z direction, but with the current density. The current density is constant. Okay, what we like to find, what is the magnetic field? Okay, the magnetic field around this uniform density function, okay, infinitely long. Okay, again, it's infinitely long, right? Because when we deal with infinitely long, we have some advantage is, so we know the magnetic field must be only in phi direction. The reason is, let's recall the Power-Savart law. The Power-Savart law is that if we have a point P, this is a current point to the problem P, we have used right-hand rule, right? So the fingers, 4 fingers point to the direction of current, okay, cross the R vector, okay, the current, yeah, cross R vector, right? This direction, some direction, is direction of magnetic field, okay? So the magnetic field must be in phi direction, okay, must be in phi direction. And also because this is infinitely long, right? So the R, for giving R, or small r, right? And this is a constant. Okay, this is constant. So in this case, when we calculate the circulation of magnetic field, we only need to calculate this DL. The DL is easy, is phi in phi direction. Okay, so this is DL. This is DL, right? Then when we have a DL, we have magnetic field, then A phi dot A phi equal to 1, then we can easily obtain the magnetic field, right? And also we need to treat differently when your observation point is within the conductor. Because within the conductor, that means when R is less than the radius A, right? The total current is depend on your R square, right? But if your R is outside of cylinder or larger than A, okay, then your total current is fixed. That is bounded by A square, the radius A square. So this is a total area times the constant current density. We know that is total current. So what that affect how we calculate the current, right? But however, this is whatever right on the right hand side, right? But on the left hand side, we have a circulation of magnetic field. Okay, the circulation of magnetic field we already calculated is this with a different current, right? But if we look at this problem from a generalized Am's law, in generalized Am's law, we deal with the two types of current. One type of current is we call impressed current. So the impressed current means the current is placed by you, okay? You apply, okay? You applied current. Let's say in this case, the current on the conductor is applied by you, okay? There is another current. That is current created by somebody else who launch electrical field. Okay, that field changes with time. This is displacement current. Okay, this is a current B type. Sorry. This is A type. This is the B type. Okay. Okay. Completely different. Okay. Right. So one is the apple, one is the orange. Right. Okay. The B type, however, must exist if you have a time varying electrical field. Okay. But in this question, I didn't mention we have this field. So therefore you don't need to worry. You don't need to consider because current doesn't change with time. Okay. Current, why describe current? I didn't say a current density is a function of time, right? It's not a function of time. Okay. So therefore, because this condition, so we don't need to consider it. So this term equal to 0. We only need to consider the normal DC current. Okay. So make a summary. So now we discussed, so far, we have discussed completely the integral form of Maxwell equations. We have Faraday's law, Am's law, okay, electrical field Gauss's law, magnetic field Gauss, right? And then from this and this combined, okay, we have arrived the conservation of charge. Okay, law of conservation of charge. Right. We also introduce two variables in addition to B and E. We have D and H, right? So D is a flux density, okay? And H is field intensity. So no matter for magnetic field and electrical field, we have both fields have a variable called flux, variable called field intensity, right? Both for electrical field and magnetic field. Not surprised, not surprised, okay? Now, for electrical field, we have a flux called D, field intensity we call E. For magnetic field, flux we call B, and field intensity we call H. Okay, and also we introduce two parameters, constant parameters. One called permittivity that relate to the electrical field. In free space, the permittivity is a constant. Okay, and for magnetic field, the permeability is also a constant. The interesting things, the velocity, the speed of light, C. So the C is related to these two parameters. So that means these two parameters is regulated, okay, is calibrated to the speed of light because electromagnetic wave, because light is a kind of electromagnetic wave, right? Okay, so that means this regulates the speed of electromagnetic wave, right? Which is this. Okay, so that perfect time. So that is clear. The very complete description of any phenomenon regarding electromagnetic waves, because I like to clean up this and then give us a very clear picture how elegant this Maxwell equation is. Okay, how elegant. So from next class, we discuss the differential form. Okay, differential form of Maxwell equation. Let's take a break. Let's take a break for 10 minutes. Okay, so let's continue on Maxwell equations. Okay, now we try to find the differential form of Maxwell equation. Still the same set of equations. So Faraday's law, Am's law, Gauss's law for electrical field, magnetic field, and the law for the conservation of charge. Right. The reason why we are interested in the differential form, because the integral form only give us, you see, integral form can be easily observed, okay, by experiment, right? You see, because integral form only give you, you see, the line integration, the line can be large enough, right? And the surface integration, you can define in a certain, you see, size, right? And then you can conduct a measurement and so on. But that only give you a kind of macroscopic description of the field behavior. Say, for example, it tells you, hey, the magnetic field has the net flux always equal to 0. right? Sure, this is a very large picture about magnetic field, right? And then say how much charge you can include it by a surface if you measure the total flux of the electrical field. But however, you see, when people want to describe a field relation, particularly to a point, okay, you tell me what is the field strength at a specific point, the relation with other sources, say, for example, current and charge, right? Or the other boundary, we call boundary conditions. Say, for example, well, I want to find the field point when I hold my mobile phone near my body, right? I like to know what's the field inside, what's the field strength inside my body, okay? That is a very difficult question if we only have a different differential form, okay? So in my career, we saw, you say, and also what I can observe, you see, from other people's research, nobody solve electromagnetic problem using integral form. But however, integral form is a good starting point, okay, by all means. So no matter what, right, we like to find the field at individual point, okay, or the vector at any given point, the field vector at any given point. So this is instead of a region in space, we want a very precise in a point. Okay, you can take this lesson as a review of mathematics. Okay, so you can see the discussion in the rest of the class today really has nothing to do with any physics. It's just mathematics. Okay, the mathematical treatment, right? So now let's look at Faraday's law. Faraday's law first. Faraday's law on the Faraday's law. The Faraday's law on the left-hand side, we deal with a line integration, right? Forget about the E, forget about the B, okay? But let's look at the mathematics, okay? Let's look at the mathematic treatment. That is a vector line integration, right? The vector line integration. So because we are dealing with field is a function of location and a function of time, right? So therefore, if this is a vector quantity, we have a 3 component. We deal with this in rectangular coordinate system. So we have X component, Y component, and Z component, and each component is a function of X, Y, Z, and the time, right? Okay. Now let's evaluate this vector line integration in a very specific, along a very specific contour, all right? How specific it is? Okay, let's look at this. We have our coordinate system, X, Y, Z, okay? Then we find a point, we call this point, sorry, this is not right, okay, this is not right. I don't like to mislead. And I should say this is my X. And the Y is somewhere. This is my coordinate. Okay, this is my origin. Okay, this is my origin. Then this point, I change color. This point is arbitrary point, X, Y, Z. This is arbitrary point in space, all right? Then I define the contour I define the first contour, that normal direction in x direction. You see my surface? My surface are defined by contour A, B, C, D, back to A. This is my contour direction. Okay, this is my contour direction. Okay, this is my contour direction. So this contour is, sure, I arranged in a differential sense. Okay, differential sense means the length is differential length, area is differential area, okay? And with a specific direction in x direction, okay? So if I evaluate this line integration along this contour, okay, along A, B, C, D, A, okay, then because this is so small, okay, the so small I call differential length. The field at this point I can assume doesn't change over this small path. Can you accept that? Can you accept that? So you can you accept that? Okay, so if you accept this, the field over this area, when I do line integration, I can say this is I take y component, this is y component. This is y component in this direction, right? Y component in this direction, the total line integration, this is the integration of this part. This is from A, B, okay? This is A, B, the integration over A, B, right? And this integration is B and C, okay? Because this is all in the positive direction according to my coordinate. So I use a positive sign in front. Okay, then this is integration also in y direction, but in the opposite direction of y, right? So this is a contribution of CD, and this is a contribution of DA. Okay, so I finished my line integration, right? Because this is a everything is a delta. Delta is not as small as differential length yet. Okay, the difference between delta and the D is this is a very, very small. This is infinitely small. Okay, this is difference. Okay, so I'm still using delta right now. Okay, delta is a very, very, very small. Small, okay, but not infinitely small. Then if I can conduct this, then I can also repeat this over the area is A so I change the color. Okay, I can go A, D, E, F, Okay, then in this case, this is my normal direction in y direction. Okay, so I can conduct this is a contribution of AD, right? And this is a contribution of DE, contribution of EF, contribution of FA, right? And so on. This is another surface is from A, F, G, B, back to A. Okay, so this normal direction in that direction. Okay, in that direction. So this is I carefully chose this tree because convenient, very convenient. Okay, and illustrative, and then reflect the essence of the problem we are dealing with. What we try to do is we apply the integral form of Maxwell equation to a differential length, surface, and volume. Okay, we shrink the volume, we shrink the surface, shrink the line to a point. Okay, now this is what we have done on the left-hand side. And here on left-hand side, we have this circle means is a closed line integration, right? But closed line integration, the surface is not closed. Surface is open surface, right? So we also is very clear the simplest surface corresponding to each of these three contours will be defined by this direction, the differential area, right? The first differential area will be this, right? The differential area. So what we deal with the differential area is we need to calculate this surface integration of B over this surface, right? Over this surface, so calculate the B. Okay, let's say the B, ABCD, right? That equal to this. So that means the first equation we have A, B, C, D, A. We deal with line integration. This equal to surface A, B, C, D, right? Then let's calculate the flux of B over this. And in this case, is this surface. Okay. The contribution. Okay. This surface, we assume the magnetic field B at the arbitrary point X, Y, Z everywhere equal. Okay, so this is a constant. Multiply this area, right? dy dz. This is dz. This is dy, right? Then this is the flux. So suppose this term equal to everywhere here. Okay. Let me clear up. This is clear. Okay. So these two equal. Okay. Why for these two equal? I have. Okay. Why I said this equal? I divide delta y times delta z on both sides. Okay. I can do this. When I divide this is cancelled, right? And then when this term divided by delta y, delta z, so delta y cancelled, I have delta z. right? Y divides this delta Y, delta Z. So delta Z cancel, I have delta Y, right? So the same as this, I have this, I have delta Z left, I have this, I have delta Y left. And the delta Y combined with delta Y, delta Z terms combined with delta Z terms, okay? We have first equation generated, okay? First equation generated. Similarly, we have second equation and the third equation, okay? I don't repeat this, right? And then, sure, you see Y equals M. I have this surface integration, and don't forget we have the original equation of Faraday's law. We have Faraday's law. We have minus sign and the directivity with time, right? This is a, I didn't forget this. I have minus sign with the directivity with time. All right, so that is our first equation. All right, and the first equation, we can similarly, we integrate over this surface. We have a second equation. When we surface integration with this, we have a third equation. All right, okay. If we repeat this, and again, we let delta x approach to 0. That means delta x become dx. Okay, delta y approach to 0, then this become dy, right? All right, so this equation become differential form. Okay, become differential form. Everything we deal with is a partial directivity. Okay, so that's why that means partial x means take derivativity with respect to x with other variables y, z, time, constant. Okay. So this is what that means, right? The partial derivativity. Okay. Actually, this is not my job. This is your mathematics teacher's job. All right. Okay. Now we can prove from integral form what the Faraday's law tells us is this set of equations. Okay. But this set of differential equation, partial differential equation. Okay, or we call PDE, right? Okay, partial differential. But okay, we can write it in a vector form. Okay, we can write it in vector form. You see, this vector form exactly equal, right? What's a vector for? People invent a vector. What's that for? You provide convenience, right? Provide convenience. If I write this vector form, when two vectors equal, what that means, the sufficient and the necessary condition is they're each corresponding component equal, right? Okay. Then we have 100%, you see, we have sufficient reason we can write these three equations into this vector form. Once we have this vector form, we can further make it more compact. Okay, more compact is when we have A cross B. Okay, we can write it in a vector form is, okay, let's write here. The vector A cross B, we can write in a determinate form. Okay, this form. Now, if you treat delta, the A equal to delta, what delta is a differential operator. What delta is defined is partial x. Okay, let me keep it simple. The AX, I just write like x, okay, simple. Okay, this is a delta is a vector. Okay, delta is a differential operator. Vector differential operator. Okay. The operator means you can use, you can activate on different variables. Okay. We will deal with this all the time, so I don't repeat this anymore. All right. Then if you treat A equal to this, B vector is electrical field. Okay. This equation exactly we can write in this way. Okay, exactly we can write in this way. Not surprised. Takes you less than 5 minutes. You can convince yourself. All right. Okay. Do you think this is a very much more compact, concise, or elegant than this? Of course. Right. Now, I don't repeat this process anymore. Okay. What process? The process is how we relate a line integration of a vector with a flux or surface integration of vector. Okay. This is what we did. Okay. Now let's look at Ampere's law. Okay. Let's look at Ampere's law. Ampere's law is what? Ampere's law also need to deal with, on one side is a circulation, a vector circulation, line integration. On the other side is a time derivative with a flux density, with a flux. Okay. Just now, what we did is S, but B, right? And just now for Faraday's law, and on this side is but if we forget about physics, we forget about the meaning of E and B, okay, and the D and the B and the E and H, forget about physical meaning. Mathematically, that's exactly the same, right? That's exactly the same. So therefore, we're not surprised. This term basically is this. This term basically is this. Let me emphasize with seeker. Not surprised, right? We don't repeat this. The only one thing we haven't mentioned is the surface integration of this, right? So when we do a surface integration, okay, then we take the essence, okay? So this, when we shrink the surface to the point, this is just a charge density. So therefore, we can very straightforward, we can convert Ampere's law. We convert Ampere's law into the differential form. Okay, the Ampere's law into differential form. All right. So having understood this, basically we already can deal with all the other Maxwell equations. But the things we haven't dealt with is two Gauss's law, right? Two Gauss's. Okay. Then you see, because we are going to use some of the important vector identity. Then before we deal with the vector identity, let's come back to the mathematics. What does this mean? Okay. What is this? Okay. If we deal with, you see, because you say, hey, what is this, Professor Wu? You already mentioned what is this? This is something circulation, something related to the circulation, right? Related to the circulation. But this is still not exactly what the definition is. Then let's look at the essence. Let's look at the essence of this operator. Okay, essence of this operator. There is a very specific mathematical name. It's called a curl, because this quantity not only used in electromagnetic field, it's almost used in any vector field. Okay, and the vector field, we give a name we call curl. Okay, we call curl. What's a curl? The definition, we have 3 lines instead of this, means this is by definition. Okay. By definition. Okay. Then by definition is defined as this. Okay. This is equal to, this is by definition. This is by definition. Okay. By definition, what that is? This is a, I always using this one. Okay. This is what is I found a piece of paper. Can you see me? Okay. The paper has a dot. This dot is a point I'm interested in. Okay. Now, so what I do is, I have a dot, I define a circle C, also has a direction. Okay, has a direction. So this direction, then I have, suppose in this realm, I have a vector field A. Okay, this vector field A, then I do the circulation of A. Dot, I have a contour C. Okay, I have a contour C. Then I have a normal direction of this surface bounded by the C. Okay, bounded by the C. Then we have electrical field, a field A. Okay, I have a field A. Sure, this field should not be intersect, otherwise the field line cannot be intersect, otherwise that means solution is not unique, right? Okay, not okay. Then I do the collection of this line integration along the closed Then, because for fixed point, the C is not uniquely defined, right? I can rotate my C. I can rotate my C with a fixed point, right? Okay. Then how I do is I rotate my C. That means my surface direction change. Okay. This surface is very small. Okay. Then my direction is changing. Then how I determine my direction of the surface is once the circulation reaches to maximum. Once the circulation reaches to the maximum, I stop. Okay, this direction indicates the circulation reached to maximum. Okay, the circulation reached to maximum. Once the circulation reached to my maximum, that defines my direction, AN. Okay, but if the C shrink to a point, what do you expect? The circulation must approach to zero. If every time approach to zero, I'm not interested. So that means I divide this circulation by its total area. Okay, this total area also shrinks to zero. So 0 divided by 0 in this case is not 0. Okay, this is the meaning of curve. This is the meaning of the curve. Okay, so how we reflect this maximum? Let's recall one. We calculate this curve. Okay, we take the component normal to the surface, right? The component normal to the surface. So that means that is the maximum flux we can collect. Maximum flux we can collect. So that means if we consider the normal component of B, when we consider the normal component of B, we consider the normal component of B, we use this surface, which is perpendicular to this B. And we know this surface will give us maximum circulation. Okay, so these two are consistent. Okay, consistent. This is our definition of curve. Okay, this is. Then in certain field, okay, the curl of vector always equal to 0. For example, if the field is like electrical field, okay, like electrical field, no matter how you define this contour, okay, the circulation always 0. But for magnetic field, okay, because you don't have an ending of the field line, okay, then the circulation were not equal to 0. Okay, so some field circulation is 0, some field is not. Okay, all right, okay. Then the mathematical expression for circulation, either we defined by, if this is in rectangular coordinate system, we already defined. In cylindrical coordinate system, spherical coordinate system, we can find its mathematical expression. Okay, so we don't derive this, and then I don't ask you to remember, but however, for rectangular coordinate system, you need. So finally, let's find one theorem we call a Stokes theorem. So that theorem I think you'll learn this in mathematics, engineering mathematics. But let's recall, this is a very clear, this relation from definition, right? If this definition say the curl of a vector is something related to curve, right? And related to the differential surface. But this is, everything is small. Everything is very small. Then we multiply this delta S on this side. Okay, I multiply this delta S on this side. Okay, then I take, also I consider this is a vector. This vector, I multiply the AN on both sides. Okay, so okay, I multiply this on both sides. Okay, then this, I can say this become vector dot. Okay, and on this side, C, right? But this is still in a differential sense. That means I'm looking at the very small cells of a large surface, but open surface. So open means they looks like a bag, right? Like a shopping bag. And then I have a mouth. This mouth define my contour C, right? So this is a differential relation. Only concern a small, very small part on the surface. But if I have many of them, I put a sigma. Okay, I put a sigma. And also this line integration, because it has a direction, right? If you have line integration for one cell, and then this is another cell, so on the common boundary, they are opposite, but magnitude equals, they cancel each other, right? So this is in infinite terms. Okay, then this become collection, become surface integration. So the delta S become ds, okay? And this on this side become a total line integration, but this is delta, and the line integration of vector A. But this C is after you cancel each other, all the internal boundary, okay? So only contribution that left, not equal to 0, is on the outermost contour boundary C, okay? So this is a Stokes theorem. This is Stokes theorem. Okay, and we will use the Stokes theory to prove some of the very useful vector identity, right? And I still owe you something is, we said the Gauss's law can be derived from the other, from Faraday's law and Am's law, okay? And that's easy to justify after we justify the two useful vector identity, and we discuss this next time. Okay, so let's have some questions today. So far, I have, let me post, because I cannot see the chat. Maybe you already post your question in the chat, right? Okay, good. I have one chat question. Okay, you can type your question on the chat. I can say it, right? If you don't like to speak out. So, any question? Or we go too slow? No answer. Too fast? It's okay. Okay. All right. Okay. Great. Thank you. Yes. Need time digest. This course, you see, I really think if 1 hour I gave in class, at least you should have 2 hours, okay, for revision, okay. And sure, you see, doing homework is a part of it, right? Doing homework, and we must do homework by ourselves. We must do homework by ourselves. Okay, maybe at the beginning, you may find it takes longer time, but if you do it independently, okay, and using first principle, learn how to use first principle, and you will do it faster and faster. Yes. Okay, so if no question, so I will stay here. Okay, I will stay here for a while, and then let's end this class. I will stop recording, and I will be here. And then if you like discuss with me, and then also over the Zoom, I'm available. All right. Okay. Bye bye.
Remember to take the attendance.
Oh yes, attendance, please. Attendance.